In June of 1902, the German philosopher Gottlob Frege was at the absolute height of his career. Then he opened the mail. He read a short, 2-page letter that immediately caused a physical and professional breakdown, forcing him to be hospitalized. The letter came from a 30-year-old English mathematician named Bertrand Russell. Russell had been following Frege's work closely, but while doing so, he stumbled across a logical flaw. It was a contradiction that threatened to tear down the massive project Frege had spent his life building. That project was known as logicism. At the time, some prominent thinkers believed mathematics was a subjective construction of the human mind. Frege and Russell wanted to prove them wrong. They wanted to demonstrate that mathematics was completely objective and that all of arithmetic could be built from the ground up using pure logic and something called sets. To build this foundation, they relied heavily on a branch of mathematics invented a few decades earlier by George Cantor. Cantor was the father of set theory. He provided the exact mathematical tools Frege and Russell needed to map out the entire universe of logic. The stakes were incredibly high. If they could successfully reduce numbers to sets, every mathematical truth would become as undeniable as 1 + 1 = 2. They would establish a permanent, unshakable foundation for science, technology, and all human knowledge. To understand how it all fell apart, we have to look at what a set actually is. Put simply, a set is a collection of distinct objects or thoughts gathered together into a whole. It takes a many and allows us to think of it as a one. The rules of this early version, called naive set theory, are incredibly loose. A set can contain anything you can imagine. You can have a set of all the cats in the world, a set of all the people watching this video, or even a set containing entirely fictional characters like Harry Potter. The objects inside don't even need to be related to one another. You can create a set containing exactly 2 things, the 4-time NBA champion LeBron James and the Roman numeral 4. These items share absolutely no logical connection in the real world, but in set theory, they sit perfectly together inside a single set. Because sets are so flexible and all-encompassing, Frege and Russell viewed them as the basic atoms of logic. They thought that if they could define every number simply as a specific set of items, they would finally have the objective mathematical system they were searching for. This system operates on a rule called unrestricted composition. That means any condition you can possibly describe automatically creates a valid set. If you can think of it, you can make a set out of it. You can even apply this to nothing at all. Set theory allows for an empty set, a collection containing absolutely 0 members. It exists, and it is defined entirely by the fact that it holds nothing. And because you can put anything into a set, you can also put sets into other sets. You can easily define a set that contains all sets with exactly 1 member inside them. This brings us to a strange consequence of these rules. Since a set can contain anything, and sets can contain other sets, a set can swallow itself. For example, the set of all sets is obviously a set. Therefore, it must be inside itself. At first glance, a self-containing set feels like a weird logical curiosity. But allowing a set to sit inside itself is the specific variable that turns the entire foundation of mathematics into a ticking time bomb. In 1901, Russell started thinking about all the sets that do not contain themselves. For instance, the set of all cats is not a cat, so it isn't in its own set. He gathered all of those non-self-containing sets together and formed a new set. Then he asked the question that broke Frege. Consider the set of all sets that do not contain themselves. Does this set contain itself? Let's trace the logic on this flowchart. If the answer is yes, the set does contain itself, then it violates its own strictly defined condition. To be in this set, an item must not contain itself. So by containing itself, it fails the requirement and must be kicked out. Looking at the alternative path, if the set does not contain itself, then it perfectly meets the criteria for membership. It is a set that does not contain itself. Because it meets the rule, it has to be included. If it doesn't contain itself, it does. And if it does, it doesn't. The set simultaneously includes and excludes itself. This is a pure contradiction. In a logical system designed to be the bedrock of objective truth, an absolute paradox like this means the entire system fails. The mathematical community panicked. To save their work, later mathematicians rewrote the rulebook. In what became known as Zermelo-Fraenkel set theory, they added axioms that explicitly outlawed sets from containing themselves, successfully forcing the paradox out of arithmetic. They managed to save math, but they did it through an arbitrary restriction. They treated the symptom but ignored the disease. The logic itself naturally produced that contradiction, and writing a new rule to ban it didn't explain why the flaw existed in the first place. The restriction feels hollow because the original rules of set theory are direct reflections of predication, the basic, everyday act of saying things about things. In any natural language, a sentence has a subject, like LeBron, and a predicate, like dunks. The relationship between a predicate and a subject is identical to the relationship between a set and its members. A predicate is true of a subject, just as a set contains an object. Because we can turn any thought into a predicate, self-containment is unavoidable in human language. Some predicates are naturally true of themselves. For instance, the phrase "is a predicate" is, factually, a predicate. It describes itself perfectly. Mathematicians can agree to restrict the rules of a highly formal mathematical game, but you cannot patch everyday language. We cannot stop using predicates to think and communicate, which means the paradox is still there, embedded in how we speak. We can recreate Russell's exact problem without a single mathematical symbol. We just need to formulate a predicate that targets all the predicates that do not describe themselves. That predicate is not true of itself. Now apply that predicate to itself. Is the phrase "is not true of itself" true of itself? If it is true of itself, then it claims it is not true of itself. It becomes false. But if it is not true of itself, then it fulfills its own condition, making the statement completely true. True means false, and false means true. When a young Bertrand Russell wrote to Frege, he exposed a crack in the foundation of math. But as an older man, Russell had to live with the knowledge that this crack ran much deeper. Russell's paradox remains a permanent glitch in the structure of human thought. The logic we use to describe reality contains an inherent flaw, one we can perfectly articulate but never actually fix.